Hi, welcome back to Statistics 1. We're up to Lecture 9, and the topic in Lecture 9 is the central limit theorem. In the last segment, I started to talk about inferential statistics and the idea of null hypothesis significance testing. And even 2 lectures ago, when we were talking about regression, I pointed out in the R output some t-values and p-values and this idea of a certain p-value being statistically significant. Well, I didn't really give you a detailed description of where those p-values come from and how we determine if a certain p-value is statistically significant or not. The nitty-gritty and the details for all of that come from this idea of the central limit theorem. So in this lecture, we'll get to the bottom of where do those p-values actually come from. And to understand the central limit theorem, I first have to introduce this idea of a sampling distribution. So there'll be 2 segments. First, we'll talk about sampling distributions, and then I'll go into the formal statement of the central limit theorem, which again provides the foundation of where these p-values come from in null hypothesis significance testing. So first, what are sampling distributions? This is notoriously a difficult lecture in intro stats. So I've been teaching intro stats for 16 years, and almost every semester this is a stumbling block. So please pay attention to this lecture closely, maybe watch it a couple of times. It's a little bit of a difficult concept to wrap your head around. So I'm going to sort of ease you through it slowly, and the way I'm going to do this is to go back to a review of simple histograms. So remember way back in the second week we talked about histograms, and they're used to display distributions. And one that I relied upon a lot was a histogram to display a distribution of individuals and their body temperatures. So if we converted everything to z-scores, it looked like this. Again, I'm assuming I have a random sample of healthy individuals, and I measured their body temperature, and then converted it to z-scores so that the mean body temperature is 0. If you prefer, I could plot it in degrees Fahrenheit, so the mean is about 98.6, or if you prefer, again, we could look at it in Celsius. Okay? We did this to look at a distribution of individuals and their body temperature. There's this natural variation. Some people are a little above average, some are a little below average, but this is a healthy sample, so no one's really, really high, running a really high fever. If a distribution is perfectly normal, those weren't perfectly normal. There's always some sampling error, right? But if it's perfectly normal, then we know the properties of the distribution. So here is a perfectly normal distribution, and again, standardized. So the mean is 0. 1 standard deviation falls about here, and 2 standard deviations is out here, and 2 standard deviations below the mean down here. So a couple things to notice about this perfectly normal distribution. One, it's symmetrical, right? So 50% of the distribution falls above the mean, 50% falls below the mean. The other thing to notice is the majority of the distribution falls within 2 standard deviations of the mean. So if you're 2 standard deviations above the mean, so up here, or 2 standard deviations below the mean, down here, you're a pretty extreme score in a normal distribution. We can use that information to make probability judgments. So the normal distribution combined with the idea of probability allows us to make predictions about the distribution. Now, keep in mind that predictions aren't certain. They're probabilistic. Again, just like the NHST logical reasoning is probabilistic, we're going to engage in some probabilistic predictions. So we're going to get p-values associated with certain questions. So for example, just talking about a histogram looking at a distribution of individuals, I could ask if one person was randomly selected from the sample, what's the probability that his or her body temperature is less than a Z equal to 0, or less than 98.6, or less than 37 Celsius. That's real easy. Z of 0 was the mean, so what's the probability of that happening? Well, it's 0.5. Half of the distribution is below a Z of 0. So the probability of that happening is 0.5. Let's make it more interesting. If one person is randomly selected from the sample, what's the probability that his or her body temperature is greater than Z equals 2? I just showed you that a very small percentage of the distribution falls beyond 2, right? So this is going to be a very unlikely outcome, and it turns out the probability is about 0.02. So this is a very unlikely event. It might make me want to rethink my assumption that everybody in this sample is healthy. Do you see now the connection to NHST? I made an assumption. I looked and calculated the probability of an outcome. I got a really low probability that might make me rethink the initial assumption. That's what we're going to do, but at the level of samples. So here I could write it out just like I did when we were talking about NHST. If the sample is healthy, then no one should have a fever, that is, run a really high temperature. But I detected a person with a fever, therefore this sample is not 100% healthy. That's exactly the logic we engage in when we do NHST. But we do it with sampling distributions, not distributions of individuals, distributions of sample statistics. So to be clear, a sampling distribution is a distribution of sample statistics obtained from multiple samples. So we could do this for any sample statistic. We could get a distribution of sample means, we could get a distribution of sample correlations, we could get a distribution of regression coefficients. The trick about this concept and why students stumble here is because we don't actually do this, right? When I do an experiment or a study, I just get one sample and I go from there. So this sampling distribution is a hypothetical. I don't actually have a sampling distribution, I estimate it. So it's hypothetical. So let's assume that I get a mean calculated from a sample, and that sample is obtained randomly from the population. And let's assume a certain sample size, n. Now, again, assume I do that over and over and over and over again. I get multiple samples. Again, we don't do this in practice. We do one sample, we calculate our statistics, we try to make inferences about the population. But for the sake of this segment and understanding the idea of sampling distribution, imagine that we do that. If I get multiple samples, then I would have multiple sample means, and they would all differ a little bit because of sampling error, right? So I would have a distribution of sample means, and those collectively would be a sampling distribution. I could do that with any sample statistic. Then I could take a sampling distribution, marry it with probability, and now you see how we're moving towards NHST. So I can say if one sample is obtained from a normal, healthy population, what's the probability that the sample mean is less than Z equals 0? Well, again, that's easy. Z equals 0 is the mean, so it's just P equals 0.5. Let's go to the more extreme example. If one sample is obtained from a normal, healthy population, what's the probability that the sample mean is greater than Z equals 2? That would be really unlikely. Again, the p-value would be about 0.02. In other words, the p-value is less than 0.05, that magic cutoff, right? Which means I would rethink my assumption that this population is healthy. I might want to reject that assumption. That's exactly what we're doing with NHST. So to be clear, in NHST we say if this population is healthy, that's an assumption, then no one sample should have a high mean body temperature. I've obtained a very high sample mean, therefore I'm going to reject that initial assumption that the population is healthy. Now, I've glossed over again a little bit of the detail in what exactly is very high and very low, and what exactly are the cutoffs, and where exactly do we get the p-values from. In the next segment, we'll walk through the logic of the central limit theorem and look at multiple sampling distributions to see exactly where those p-values come from, in particular in the context of regression. But for this segment, just understand what a sampling distribution is. It's a distribution of sample statistics obtained from multiple samples, assuming that they all have an equal sample size n. And again, remember that this is a hypothetical idea, this sampling distribution, but we need it to engage in null hypothesis significance testing and to obtain p-values and make probability judgments about samples. And again, we can get sampling distributions for any sample statistic, the mean, a correlation, or a regression coefficient, and lots of others going forward in the course.